Hi everybody. We'll be talking about unsupervised learning of sentence embeddings and in general, and our own model Send2Vec in particular. So I'm Prakhar, this is Matteo, and unfortunately Martin is not here. So moving on, I would like to put the idea of sentence embeddings in some context. So the sentence embeddings have been inspired by the success of word embeddings. So what are word embeddings? So word embeddings are the mapping, or you can say representation of each word into an n-dimensional feature space. It is something that can be, you can say, vaguely understood by the computers. So this uses the context hypothesis, which says that if two words fit well within the same context, they must be similar. By the context, I mean the neighborhood. So, as you can already, you must have already seen by in the presentation by Jan, that if two words are similar, they should occupy nearby positions. So, in this case, you can see that lion and giraffe, which are like wild animals, occupy a closer position as compared to the pet animals or household items like mug and cup. In general, to denote the distance between two words, we generally use the cosine distance, or we can also use other metrics like Euclidean distance. So, moving on, why do we need word embeddings? So, it has been seen that word embeddings are very useful in pre-training to improve the performance of a lot of NLP tasks. They are also useful in finding the semantic distance between two different words, as you have already seen in the presentation by Jan. And some very well-known word embedding methods are Word2Vec, Globe, and FastText. These models are very fast to train and are unsupervised. So you just need some raw text and that's it. Voila, you get the corresponding representations of each word. As a result, they have been widely adopted in both academia as well as industry. So inspired by their success, we have sentence embeddings. So in case of sentence embeddings, what we try to do is, instead of mapping a single token, we try to map short sequences of text, like sentences or paragraph, to an n-dimensional feature space. So again, why do we do this? First of all, it eliminates the need for feature engineering. You get sentence features that can be fed to different machine learning classifiers and use them for different downstream supervised tasks like sentiment analysis or question answering. Another important use is you can use these embeddings to gauge how similar two sentences are. So the big question is, what is the thing that really imparts the meaning to the sentence? Is it the context, that is the surrounding sentences? Is it the content only, which is the words in the sentences, or is it some sort of structure? So what we claim is that it's all three combined together which give the sentence its meaning. And as we move on, you'll see that our hypothesis is validated. So we'll do a brief recap of already existing sentence embeddings. So the first model is skip thought vectors. So skip thought vectors is a recurrent neural network. To be more specific, it's a GRU. As Jan told you, it's basically a toned down LSTM. So in this case, the model, when given an input sentence, is trained to predict the next and previous sentences in a text. This model has shown very good performances on supervised tasks and hence is very powerful. However, this model takes a lot of time to train. It's very computationally very intensive. In fact, for the state-of-the-art model, it takes around 2 weeks on GPUs to train it. Also, it suffers from a very poor performance on similarity evaluation tasks. And another major drawback is that it needs an ordered pair of sentences. That is, in the text, every sentence must be the logical continuation of the previous sentence. So, if you have a data set like tweets, well, your model will fail spectacularly in this case. Another important model, one of the earliest models is Doc2Vec or Paragraph2Vec. So it's a very simple log linear model. In this case, basically what you do is you try to learn a paragraph vector And this model is trained in such a way that you take the paragraph vector as well as the context words of a word, the neighboring words of a word, and try to predict the word itself. This method is, and as a result, you end up learning the paragraph vector. This method is very fast to train. It can use any corpus. So just in case if you want to train it on a domain-specific corpus, go ahead. And this method is very versatile, as in it is works well with text of arbitrary lengths. So let's say if you have a whole document, a paragraph, or a sentence, it will generate embeddings corresponding to them. However, this method performs very poorly again on both supervised and unsupervised tasks. As well as for each paragraph vector, you need to learn the paragraph vector and store it in the memory. So this model has a very high memory footprint and is unable to scale well. So another method, another new model that has been proposed is FastScent. So it's based on a similar idea as skip thought. However, it tries to be computationally efficient by using a simple and shallow neural network. And you can augment this method by trying to predict the content of the sentence as well. This method is fast to train and is also very fast when it comes to inferring the corresponding sentence embeddings. However, unlike skip thought, this method doesn't perform well on any of the tasks. And like skip thought, it requires an ordered corpus. So far we have seen methods which require context, like the skip thought, methods which require content, like the paragraph to vec, and methods which require both, in the case of FastScent. What about structured data? So here is the another model, DicTrack. So this model tries to align the dictionary definitions in the form of sentences to the corresponding word embeddings. This method performs really well, but the downside associated with this method is that it requires a large number of dictionaries. Hence, it's not very suitable for specific domains. Another very nice method of getting sentence embeddings is that you can just compose and average the corresponding word embeddings, and you get a corresponding sentence embedding. This method is very fast to train. In fact, you don't need any training at all once you have the word embedding model. Also, it can be trained on any corpora, and the best thing is it acts as a good baseline to compare other sentence embedding models. And yeah, this model doesn't perform well as well. The last model that we'll be talking about before going on to our model is C-phrase. So the interesting thing about this model is, instead of using a raw text, this model uses past corpus and tries to learn the embeddings corresponding to past constituents. That is, all the subtrees present in the parse tree of the sentence. This method is faster than the skip thought vectors, performs very well on unsupervised similarity evaluations, and it's very fast when it comes to inferring, because you don't need any parse information during the inference, you just average it, and it can be trained on any specific corpus. So we'll be moving on to our model, Send2X, and Matteo will take it.
Sorry for pushing. Okay. So now our models. So maybe you saw that all of the diagrams for all the previous models that have been presented were quite similar. And so it's because they are already trying to do the same thing. So they are trying to get all the input features for the sentences, create a representation for it, and then try to do some prediction. We saw that prediction could be about content, context, or trying to hijack a dataset to get some features or to get some label like a DicTrack did with dictionaries. So what we are doing here is very similar. We are just doing the average of all the n-grams in the sentence. So in this case, we're doing the average of all the unigrams plus all the bigrams. This is so you can do it with only unigrams if you want. We also experimented with up to 3 grams. But in the paper, we reported some results for the unigrams alone and unigrams plus bigrams. The training is done by predicting the content, which is not something new as well. So what you do is you just have this sentence, like the cat sat. You pick a word, and you kind of remove all of the other features that depend on this token. Like here, we remove all the bigrams that depend on this feature as well as the unigrams, and we try to predict the missing word. And so this method is very similar to something that is well known, which is the SIBO word embeddings. but we are doing a few things that are different from SIBO. So SIBO is using input sentence subsampling, which is kind of removing some syntactical features that we want to keep. Also, SIBO uses dynamic context windows. This kind of making the prediction task very local. In our case, we don't want the prediction task to be local because we really want to accumulate the information. We want to learn how to compose embeddings of n-grams over the entire sentence. So maybe we can skip this one at that time. So if you want the training specificity, just go to the paper. We can talk maybe after. So the evaluation is done on two types of tasks, supervised task and unsupervised task. So supervised task is really simple. We take your embeddings for our sentence, we just push it through a very simple algorithm like a logistic regression, and we try it on some like supervised learning setup for express sentiment analysis. For unsupervised task, we have a data set containing those kind of pairs of sentences with human annotations. For example, a large cat is drinking milk, which is quite similar to a lion is drinking water. So what we want to do is to compute embeddings for those two sentences, compute the cosine similarity, and then checking that the scores that we get are actually correlating with the human annotations. And those are the scores here. So what you can see first. So you can see supervised average, which is the average of all the results for the supervised task. The unsupervised average, which is the same thing but for the unsupervised task. And the macro average. Macro average is the average of averages. And this is the global metric that we are using to kind of run the method. You can see that our methods, Sun2Vec, are always at the top, which is good. If you look at the method that should be in red, but they are just blurry right now, sorry. They are all trained on the same data set, so much that we can really compare well. And you can see that we have a 3.8 percentage point improvement over like the state of the art. Also, we said that the method was quite similar to SIBO, but actually we are like a 3.8 percentage point better than SIBO. And on all data sets, even the ones that kind of hijack data set to kind of get some labels and do in the semi-supervised setup, we are 2.2 percentage point better. So our model is extremely fast to train. We are doing very fast inference as well because we're just averaging things, so it takes no time. We are good on both supervised and unsupervised tasks. We can be trained for specific domain, which is extremely important for the industry because, as it has been said this morning, the need of the industry is not always the same as the need of academia. And but then the model can lack a bit of expressiveness. Okay. So for instance, features need to be additive, of course, because we are doing averaging of input constituents. So if you have this sentence, the house was large, comfy, and full of light. Here, you can understand that the house is what? It's large, it's comfy, and it's full of light. So everything adds up together, and it's working well. But features are not always additive. They can be more multiplicative, like negation, for instance. The house wasn't blue or green, but red. Here, your embeddings, you want it to represent the fact that the house is red, and not something else. If you use our embeddings, because we are using additive, we're just adding things together, you will get an embedding which is kind of a mixture of all the colors. So it's not still perfect. Also, we don't take into account like a unknown word, so if we cannot understand all of Trump's tweets, so but we're working on it. Finally, maybe to conclude, we introduced a new model to test state-of-the-art sentence embedding. All the code is on GitHub, all the published models are also there, so you can play with them if you want. It's extremely fast to train, which is very good for the industry. And when I say very fast to train, it's like, for example, I think the biggest data set that we trained on was 230 gigs. It takes maybe like 15 hours or something. So it's very, very fast. It can be doing on domain-specific corpus, which is also a very good asset. And of course, there is some space for improvements, but we're working on it again. And so that's it. Any question?
Time for a couple of questions. Yes?
Just because you were really fast on this, did I get it correctly that your algorithm does not consider the sequence of words in the sentence?
It's so we kind of push sequence information under the form of n-grams. So you consider bigrams, trigrams, and then, but we don't consider like the entire sequence. It's not like a LSTM that you just read the sentence entirely.
So we basically get the local word order in take the local word order in account, but when it comes to like let's say a large window, then the word order information is missing.
Yes.
Would this work with dependency parse trees? Like, could you build n-grams by traversing a dependency parse?
I think this was the idea behind C-phrase.
Yeah. So this is also one of the ideas that we're exploring. So instead of using n-grams, what you can do is maybe you can use the units, the constituents of a parse tree, instead of n-grams. So the thing is, some n-grams don't have any meaning at all, they don't make sense. But when it comes to a parsed tree, the parsed constituents do make some sense and do convey this, some information about the structure. So this is also one of the ideas that can be built upon.
Yeah.
So related to the size of the corpus to be trained, suppose that you apply your method to a specific domain.
Yep.
You think that in order to have good results, good training, how big should the corpus be?
That's that big actually.
So
So
it
if you
depends.
can you just show the slide with the result? There is a number of words in it. Just a table, this one, yeah. So you can see we train on 3 different corpora. So we have the Toronto books, which is quite a small one. We have Wikipedia, which is a bit bigger, and then we have a set of tweets, which is much larger.
So the Toronto books was like around 13 GB, and you can see the training time in ours was 1 hour for only unigrams and 1.2 hours for unigrams plus pigrams. Of course, we used multi-threading, but we don't need any GPUs or anything.
Ah, just
What's the size of the vocabulary?
So we are kind of generous. We have like maybe 1 million token, no more than 1 million token. For instance, 1 million token for Twitter, for Wikipedia, maybe something a bit less, and for the book corpus, again, a bit less.
You have 1 million different words.
Yeah. Yeah, we are. I mean, why not? Like it's Twitter, you will be surprised what you can find in tweets, really.
Okay, we have to move on to the next talk now, and let's thank the speaker again.